Okay, so we're continuing our review problem, and I want to remind you that we're looking at 3 surfaces here and 2 vector fields, which we haven't used yet. So we've only been discussing sort of geometric aspects so far, using the surfaces, finding the length of the intersection curve, the area of the intersection surface, and so on. Now we're going to throw in these 2 vector fields into the problem. And let's do that. So we were in part E. So let's write it. We're going to use some calculations that we did in the first part of this clip. Okay. So part E is find the work. This is dead. Find the work of the field F along the curve gamma from part C oriented counterclockwise when viewed from above. So remember that our curve gamma was the intersection of A and B. This now it's the curve, the intersection of the cylinder and that tilted plane, and now we're orienting it counterclockwise when viewed from above. So this is the direction, and now we have this force that was given in the data of the problem, and we want to find the work done by this force. This field F is now representing a force along gamma and moving a particle along gamma. Okay, so how do we do that? What is the work? Integral is good, but try to be more precise. The line integral of the field, right? So what we want to find is the integral over gamma. Gamma is a closed curve of this field F dot dr. Do you agree that this is what we're looking for? This is what we need to calculate. Okay, so you can call this a word problem and then freak out, or you can say, hey, this is just another way of saying calculate this, right? Okay, so let's calculate that. What do we need in order to calculate this? We need the force. We have that. We need this dot dr, which is encoding take F dotted with r prime and then do the integral. And r prime is born from the parametrization, right? So we need to parameterize this, but we already did that. And we already found r prime, so we're going to use it. Okay, so let's recall that, so let's write it here. So it's on that board. Look over here a second. This was part C. This was the parametrization of this curve gamma. This was r prime. Okay, remember this? So this is what I'm going to use. I'm going to take these components of r prime and dot them with F calculated on R. Okay, so this is X, Y, and Z that I have to plug into F when I calculate it on the curve. Okay, I'm not going to jump back and forth between these 2 boards. Is it clear what I'm going to use? Okay, so let's do that. So I have the integral between 0 and 2 pi. Let's move gamma out of the way. Here's gamma. From 0 to 2 pi d theta. And now I need F calculated on the parametrization. So let's recall what f was. F was, over here, y minus x, x times z minus 4. Okay? So I'm going to plug in the parametrization of y, of x, and of x and z. Okay? So the first component of f, the p component, was y. Y was 5 sine theta on the parametrization. 5 sine theta. This is p. Then I have the q component of f, which was minus x. On the parametrization, it's minus 3 cosine theta. This is q. And then I have the r component of f, which was x times z minus 4. This is no way going to fit here. Well, you're going to use 2 lines. Okay. So the r component of f was x times z minus 4. X is 3 cosine theta. And z minus 4 is 4 cosine theta plus 4. That's z minus 4. So all of this is r. Do you agree? Okay, the components of f calculated on the parametrization of gamma. Dot r prime. So all of this is inside the integral. This dot comes here. So dot r prime. So r prime is minus 3 sine theta, 5 cosine theta, and minus 4 sine theta. So all of this is r prime. Clear? And then here I'm going to add a big parentheses and another one here and add d theta. Everybody good? So I'm just using directly the definition of a line integral of a vector field. This is the field evaluated on the curve, on the parametrization, dot the tangent vector. Okay? And now it's just a bunch of calculations. So let's do it. So this meets this, plus this meets this, plus this meets this. Okay, let's write it all. So everybody with me? Okay, equals. So you have the integral from 0 to 2 pi. 5 sine theta times minus 3 sine theta is minus 15 sine squared of theta. Minus 3 cosine theta times 5 cosine theta is minus 15 cosine squared of theta. And then we have that long expression. So what do we have there? In fact, it's less scary than it seems. So let's look here a second. The plus 4 and the minus 4 cancel out. So here we have 12 cosine squared times negative 4 sine. Okay, so we have 12 minus 4, so it's minus 48 sine cosine squared. Minus 48 sine cosine squared. Oops, sine theta cosine squared of theta, d theta. So just like all the integrals in this course, it collapses to just being a single variable integral at the end, a regular Calc 1 sort of thing. Equals. So the first observation is that this thing is going to be 0, right? Because what's the antiderivative of sine theta times cosine squared of theta? Right, it's going to be cosine cubed up to some scalar, right? And evaluated between 0 and 2 pi, same value, this is going to be 0. Okay? If you don't see that, if you're not certain about it, if you're concerned, spell it out. Add the extra line. It's worth it. In fact, I would do it. I would just do it on an exam. I wouldn't do this at all. Okay? Does everybody agree? So what we have here is minus 15 sine squared plus cosine squared, which is 1. So I can pull the minus 15 out, and I have the integral from 0 to 2 pi d theta, which is minus 30 pi. Questions? Everybody good? Okay, so that was part E. Find the work. The work is just the line integral. Okay, part F is a rather technical short part. So part F was calculate the curl of F. So how do we calculate the curl of F? It's again just a determinant. And in fact, writing it like this is a very big hint at exactly what we need to calculate. So it's going to be I, J, K. The components of this nabla operator, which are the derivatives with respect to x, y, and z. And then the components of f, which were y minus x and x times z minus 4. Everybody good? So let's do the calculation. So in the I direction, I have the derivative with respect to y of this. This is y-less, so it's 0. Minus the derivative with respect to z of x, which is again 0. So in fact, the I component is just 0. Do you agree? J component, the derivative with respect to x of x times z minus 4, which is just z minus 4, right? Minus the derivative with respect to z of y, which is 0. So it's just z minus 4, but it's in the j part, so we need to throw in a minus, right? Plus, minus, plus. So it's 4 minus z. And then in the k component, we have the derivative with respect to x of minus x, which is minus 1, minus the derivative with respect to y of y, which is 1. So it's minus 1, so it's minus 2. Do you agree? Everybody good? Do you find something interesting happening on the board right now?
Everything here is interesting.
Exactly. This is precisely the other field given in this problem. Okay, here's the data of the problem. We had two fields, F and G. Here's G. So in fact, G is just the rotor, or the curl, of F. Okay? Does everybody agree? Good? Okay. So that's part E. Sorry, part F. So now part G. Part G, let's write it here. So part G, find the flux of G, of the field G, through the surface S from part D. In the upward direction. Is this spelled correctly? Okay, so the surface S from part D was just this elliptic disk lying diagonally as the intersection of the plane with the cylinder. Remember that? Okay, so this was the surface S. And we want the flux of the field G going through this surface S. Okay? And again, you can think of this as a scary word problem and be intimidated and leave. Or you can just remember that what is flux of a field? It's just a surface integral, right? Okay, so what we need to calculate here is the surface integral over the surface S of the field G dot ds. This is it. Do you agree? Okay. And now there's more than one way to do it. You can do a direct calculation of the surface integral. We'll do that in a second. It's not that hard. Or if you happen to make some wise observations, and that's always good. When you get a problem, before you tackle it with all the tools at your disposal, take a step back. I'm going to look at the board. Take a step back. Look at it a second and think. Maybe there's some shortcut. Maybe there's some wise thing you can do that would save you some work, save you some calculations. And in this case, it was actually kind of given to you in a spoon. So remember what G is. We just found in the previous section that G is the curl of F. So what's written here is, this is using part F, G is just the curl of F. So we're looking for the surface integral over this tilted disk of the curl of F dot ds. Right? And when you see a surface integral of a curl, what hops to mind? Stokes' theorem. Right? Stokes' theorem exactly addresses surface integrals of curls. Okay? And what does Stokes' theorem say? So this is by Stokes. That if a bunch of conditions hold, and we'll verify them in a second, because we're going to use a theorem, we're going to verify the conditions, then the surface integral of the curl equals the line integral over the boundary. And what's the boundary of this surface? It's precisely gamma that we've been using in part C and in part E, I think it was. Okay, so if this is S, then this is gamma, and it's precisely the line integral over gamma, which is the boundary of S, but not of the curl of F itself. Right? That was Stokes' theorem. So it's this. Do you agree? And this we calculated. This was part E, and so this is from part E, and what did we get there? We got minus 30 pi. Good? One more second before the questions. We're using a theorem here, and this is crucial. You use a theorem, you have to verify the conditions. Okay? So what were this is just the formula of Stokes' theorem. What are the conditions? So the field, first of all, that you're looking at has to be C1, right? Has to be with continuous partial derivatives. And it is. The field F was what? Y minus x, x times z minus 4. Everything is C1 there on the entire plane. So that's okay, right? And then there are some compatibility issues between the surface and the boundary, right? So we want the surface oriented in the upward direction, so we want the normal going this way. We have to verify that the orientation of gamma is compatible. And what's this compatibility? We called it positively oriented. So you can think of the right-hand sort of way, that if you trace gamma, your thumb should be pointing in the direction of the normal to the surface. That holds. Or you can think of the left-hand rule, where if you walk along gamma, your left hand is pointing in the direction of the surface, when your head is pointing in the direction of the normal. That holds as well. So all these compatibility conditions hold, and that you do have to write. Okay, so you have to mention the conditions. In short, don't write like a full paragraph of blah blah. In short, write F is C1 and gamma is positively oriented. Okay? So conditions hold. What we just said. Good? In fact, you can even add that gamma is piecewise smooth and so on and so forth. But the essential conditions are this compatibility conditions between the surface and the boundary, and the smoothness assumptions on the field. Okay, good. Questions about this? I want to solve this directly as well. I want to do another solution of the same problem, which is going to be longer because here I didn't have to calculate anything because I based everything on previous calculations. Okay? Questions about this? Good? Okay. So alternatively, we can calculate directly. So the surface integral over the surface S of the original field G dot ds. How do we do a surface integral? We have to parameterize the surface, right? Parameterize the surface, and then take G calculated on the parametrization, dot it with the normal to that parametrization, right? That's how we do it. And again, in fact, there's still some work that we already did. Okay, we already know how to parameterize it, and that's again, well, that's not in part C, that's in part D. Okay, so it's no longer on the board, so let's just write it here. Let's do a short side calculation here. So in order to calculate it, we need G dot the normal. This is what's going to go into that surface integral, right? So what was G? G was, I'm going to tell you because that stuff is no longer on the board. G was, the components of G were 0. So here's G, 0. Then there was 4 minus Z and negative 2. So the 4 minus Z I'm going to leave here, and then there was negative 2. And now I need to put in 4 minus Z there, but it's not just 4 minus Z, it's calculated on the parametrization. Okay? And the parametrization that we had, let me remind you, R of rho and theta equals, the parametrization was 3 rho cosine theta, 5 rho sine theta, and 4 rho cosine theta plus 1, or 4 rho cosine theta plus 4. Doesn't matter. Oops. Okay, so this was our parametrization, and now here for the G component we need 4 minus Z. So 4 minus Z is 4 minus this thing, so it's minus 4 rho cosine of theta. This is the field G evaluated on the parametrization, and now we need to dot that by the normal. And the normal was to this parametrization. We calculated it. I'm going to write it, and you're going to say that it looks familiar. It was minus 20 rho, 0, and 15 rho. This is what we had. Okay, remember that? Check in your notebooks that I copied everything correctly. Okay, so when we dot these, what we get is actually very user-friendly, because this 0 kills this minus 20 rho. This meets a 0 as well, so all we have here is minus 30 rho from the z components. Okay? Good? So that's g dot n, and now this is what we have to plug into that surface integral over the realm of the parameters, which was rho between 0 and 1 and theta between 0 and 2 pi. So what we get here, I'm back here, the integral from 0 to 2 pi d theta, the integral from 0 to 1 d rho, and then here I have this g dot n, which we just calculated was minus 30 rho. Good? So this is a direct calculation of a surface integral. And again, in this step, I use the fact that I already calculated the normal in the parametrization in the previous section. Okay? Okay, and now it's a very easy integral again. There's no theta, so the integral from 0 to 2 pi contributes to theta. The rho becomes a rho squared over 2. Evaluated between 1 and 0 contributes a 1/2. So we have 1/2 times 2 pi, which is pi, times minus 30. So we have minus 30 pi, same answer, of course. Questions? Everybody good? Okay, wonderful. Okay, so here's the last section for this problem. So in fact, this problem was written by a colleague of mine. His name is Asaf Hari, and I think it's cool. I think it's a very good review problem. I think he originally intended it to be an exam, just to be a complete exam for this course, since it covers everything. But he didn't give it eventually because there's a problem with an exam like this. That everything is based on previous sections, and if you mess up at part A, then everything collapses, and that's not a good idea for an exam. You want the questions to be separate so that, like, a small error doesn't propagate throughout the entire exam. Okay, so here's part H, which is the last part for this. Find the flux of G, of the given field G, through the part of A bounded between B and C. In the outward direction. So what we're looking for is there's this field G that is defined on the entire R3 space, and we have this, the part of A bounded between B and C is this thing. So this is B, this is C, and the part of A is the cylinder. So what we're looking at is just this, the part of the cylinder, this thing, just this. Not the solid without the inside, just this thing. Is it clear? You can imagine this, I don't know, roller coaster or something like that. Okay, clear? Everybody? Or imagine, remember in what was it? Which one was it? It was Little Red Riding Hood, where the wolf disguises himself as grandma. And then he wears this handkerchief. That's the handkerchief. Anyway, okay, is it clear what the surface is? Okay, and it's just this, without the two caps, just the outer part, just the part of A bounded between B and C. Good, everybody? Okay. So again, what we're looking for is, we need to call it something. S, we called S something different, so what are we going to call it? Let's call it S sub A. And there's a reason. So this surface is S sub A. And what we're looking for is the surface integral. We're looking for, right, the flux of a vector field through a surface is just the surface integral. So we're looking for the surface integral of S over SA of G. Do you agree? And there are several ways to solve this. Okay? One way to solve it, for example, and we'll do more than one solution. One way to solve it is to say the following. Okay, let's close the surface S, SA. How do we make it a closed surface? We have to add the two lids. The lid on the bottom, which is just this ellipse in the xy plane, and the lid on the top, which is this ellipse on the tilted plane. And then it becomes a closed surface. Okay? For the closed surface, we can use Gauss's theorem. And that's a good idea because remember that G is a rotor, right? G is the rotor of F, the curl of F. And we know that when we calculate the divergence of the rotor, we're going to get 0. That's something we've seen. Okay? So basically, this is going to boil down to calculating the surface integral on the two lids. One we already did, that was part G, and the other is very easy. It's lying in the xy plane. Okay? So is the idea of what I'm going to do clear? Let's do it. Okay? So let's close SA by adding SB and SC as follows. So SA was this thing. SA was this thing. And let's point the normal, right? We want the outward direction of the normal on this thing for SA. And now I'm going to add, let's take a couple of colors. How about purple and orange? And I'm going to close it by adding SB. SB is going to be the top part. SB is going to be this lid here. And I'm going to add it with the normal pointing in this direction. So that's SB. SB in purple. And SC is going to be the bottom lid. And I'm going to add it with the normal pointing downwards. And why am I doing this? Directions to the normals. So that's SC in orange. Why do I want the normals pointing in these specific directions? Because once it's a closed surface, I want all the normals to point outwards. Those were the compatibility conditions of Gauss's theorem. Remember? Okay. So now we have all these. And let's write. So now this equals, let's call the entire thing, let's call it S. Okay? So this thing, let's write it separately. So the integral over S, and I'm not going to write g dot ds, g dot ds, it's always the same thing, equals the integral over SA plus the integral over SB plus the integral over SC. Because S is comprised of these three surfaces. Good? So is it clear what S is and what SA, SB, and SC are? Okay. On the other hand, this equals, by Gauss's theorem, the integral on a closed surface, let's write G just here, okay, let's be more careful here. So on the other hand, the integral over S of G dot ds on the closed surface, on the entire closed surface over there, equals the integral over S. G was the rotor of F, of the rotor of F dot ds. And on a closed surface, the integral of a field on a closed surface equals, and here I'm using Gauss's theorem, equals the triple integral over the volume, over the solid, which this surface is the boundary of, and in this case we can call it V, because in fact it was called V, right? V was this solid, of the divergence of this field. That was Gauss's theorem. The divergence of this field, and in this case this field is itself a rotor. The divergence of the field, and the field in this case was a rotor. Okay? And this is 0. This is 0 because we know that the divergence of a rotor is 0. That's a straightforward calculation that I think I left as either we did it or we left it as a very easy exercise to do. Okay? So now we know that this is 0. Therefore, what we're looking for equals minus this, minus this. Okay, we'll write that on the next board and calculate these two. But before that, I just want to mention, you're using a theorem, you have to justify. So what were the requirements of Gauss's theorem? The field itself had to be C1. Okay, so the rotor of F has to be C1. Okay, and it is, because the rotor of F is G and G is C1. That's fine. Okay, and there's the compatibility on the geometric objects involved. And in Gauss's theorem, the compatibility is that when you look at the solid, the surface is the boundary. That's fine. The surface is the boundary of the solid with an outward pointing normal. And we set these normals in such a way that they are. Okay, so Gauss's theorem holds. Good? Okay. So this might look very sophisticated, but in fact we did an example very similar to this, and it's standard. It's really a standard sort of procedure. Take a surface, close it, use Gauss. Okay? Okay, so at this point we know that this on the entire surface is 0. That's this calculation. Therefore, the sum of these three is 0. Therefore, the one we're looking for is minus this, minus this. Is that clear? So let's add it here. This equals minus the integral over SB of G minus the integral over SC of G. Does everybody agree up to this point? Okay, so all of this is the justification for this step. Good? So there's still a bit of work to do. Now we have to calculate these two integrals. So we worked a bit and traded 1 for 2. That doesn't seem like it's a good trade, right? But in fact, this we calculated. This was part G, right? This was precisely this integral, the flux through the top lid. Okay, so this we calculated, and this is easy. We'll do this in a second. So let's rewrite this. So let's recall what we have. The integral over SA of g dot ds equals minus the integral over SB, the top lid, of g dot ds, minus the integral over SC, the bottom lid, of g dot ds. This we calculated in part G. It's still on the board. It's precisely this, right? And we saw that it equals minus 30 pi in this direction, in the upward direction. So it fits. So this was minus 30 pi. I'm going to write it over there. And there's also this minus here. So it's minus 30 pi minus this integral over SC of g dot ds. Good? Okay. So now it remains to calculate the integral over SC. And you can do it in various ways. So let's write it's 30 pi minus. Okay, so what is this integral? So now we're looking at, remember, SC, we had it in orange. SC is now just this bottom lid lying in the xy plane with a normal pointing downwards, right? And we want to calculate the surface integral over, this is SC. We want to calculate the surface integral of this field over it. How can we do it? We can either parameterize it. Okay, what would be a parametrization of this thing, for example? Okay, you can do it in the r theta or rho theta choice, or you can just say this is parameterized by xy0, right, where x and y belong to the ellipse. Do you agree? It's the graph of the constant zero function, fxy equals 0. Do you agree? Okay, so you can parameterize it either way. Let's choose one. So do you want to do the theta rho? Let's do the theta rho. So r of theta, or rho theta, in fact, you can even do it like we did. Oh, that's even neater. We can do it like we did part G. We can use Stokes. That's even shorter. Okay, there are several ways of doing this. Let's choose one. Let's do it like we did part G. So this integral of G, I can replace by, remember the G is the curl of F in this problem. Right? Do you agree? And the integral of a curl, I can use Stokes again. So what do I get? I'm just carrying the 30 pi minus, that's because it's part of something else, minus, and now I get the integral over the boundary of this SC. I don't want to call it gamma, let's call it big gamma, of, if this was the curl of F, so here I just have F. Do you agree? Okay. Now I have to be careful with the directions. Remember, the normal is pointing downwards, so now I have to go along gamma clockwise when looking from above. Okay, so I have to go in this direction. This is now gamma. Do you agree? Because the normal is pointing downwards. Okay, or if you're walking, you're going to walk with your head down. Think Australia. You're walking with your head down, and your left hand should point in the direction of this is tricky. Good? Use your hand. Your right hand. Not your left hand. Right hand. Left hand. Good? Everybody? Okay. So what do we get? We're still going to have to parameterize, right? So now we're parameterizing just the curve So what's the parametrization of the curve gamma? It's going to be r of theta, which is just 3 cosine theta, 5 sine theta, and 0, right? 0 for the z because it lives in the xy plane, right? And now r prime of theta is what? Minus 3 sine theta, 5 cosine theta, and 0. Good? And now I need to plug everything in there. So it's 30 pi minus the integral from 0 to 2 pi, from 0 to 2 pi, but when I take it from 0 to 2 pi, I'm going counterclockwise. Do you see that? Because I start at 3, 5, and I go counterclockwise. This is, sorry, I start when sine is 0. I start as 3, 0, and I'm going towards 5, 0, 5. Do you see that? Okay? So I wanted to go clockwise. I have a choice. Either I can say, okay, you're going to integrate the other way, add a minus sign, making this minus into a plus. That's fine. Or I can go from 2 pi to 0. That would also make it go the other way and would have the same effect on the calculation. Do you agree? Okay. So I'm going to make this into a plus, and this is because we're going clockwise when looking from above. Clear? These little details do make a difference. You have to pay attention to these little details because that's what these theorems require. Okay, if you don't add that minus, you're going to get a different answer here. Okay, so the integral from 0 to 2 pi, and now we need the components. So the components of f on the parametrization, f was, what was f? F was y minus x and x times z minus 4. So y is 5 sine theta, minus x is minus 3 cosine theta, and then x times z minus 4. Z is 0, so it's 3 times minus 4, so it's minus 12 cosine theta, x times z minus 4. So these are the components of f on the parametrization. Dot r prime, right? So dot minus 3 sine theta, 5 cosine theta, and 0. And all of this d theta. Good? So what do we get? So this times this is minus 15 sine squared minus 15 cosine squared plus 0. So we get minus 15. So the integral from 0 to 2 pi of minus 15 d theta. And that's just minus 30 pi. 30 pi minus 30 pi wow. Good? Okay, so this is an example of where you have a conservation rule in the background. Whatever way you choose to solve this, you're going to have to work a bit. Okay? So I recommend trying to solve it in different ways. I'm going to do one more solution. Okay? But there are others. So for example, even for this calculation of just the surface integral through the lid on the xy plane, this SC with downward pointing normal, you can do it the way we did it, converting to a line integral by Stokes, or you can just calculate the surface integral. You can parameterize this, and we said you can do it in two different ways, either xy 0 or with the r cosine and rho cosine and rho sine, and then calculate the surface integral. Okay? Everybody good? Okay. I want to go back to the original part h and solve it in a completely different way. So here we used Gauss. Okay, so what is use Gauss? We said, okay, we have an open surface, close it. That's what we did. And then Gauss allows you to convert to the triple integral. Okay, only for closed surfaces. Gauss only applies to closed surfaces. Okay, so that's one way of doing it. Here's a different way of doing it. I'm going to take this and close it only from above. Okay, so now I have this roller coaster here. Here's the train riding. And I'm going to close it only with a lid from above. What I'm going to get is an open surface, because I can still put my hand through the bottom, right? I didn't close it from the bottom. So it's going to be an open surface. And then I'm going to use Stokes. The surface integral on the open surface is the same as the line integral over the boundary on the bottom. Do you agree? Let's do that. So here's an alternative solution for h, another solution for h. So we're going to take the original surface, which looked like this. This was our SA. And we're going to close it only from the top. We're only going to add what we called SB. So here's SB. I'm still going to point the normal outwards. And here's SA. So add only SB. Okay? And now we have a closed, an open surface, because it's open down here on the bottom, right? Open on the bottom. Now we can use Stokes. So the surface integral of G dot ds over, let's write it SA union SB. That's the surface, the black and the purple. Good. So this is the same, first of all, as, I'm not changing anything in the surface, but instead of G, I'm going to write curl of F. Right? And now by Stokes, this surface, do you see that this is an open surface? Do you agree that now if I take this bottom curve here, just this, goes in the back, just this, and call it gamma, then Stokes says precisely that this is the line integral over the closed curve gamma of the field for which it's a curl, F dot dr. Do you agree? And in which direction does gamma have to point here? Does gamma have to be oriented? Well, again, I'm using the same rule. When I trace gamma, the thumb has to point in the direction of the normal, so now I'm going on gamma counterclockwise. Now I'm walking with my head up, going in that direction. Good? Everybody good? The normal to this surface is now pointing outward, so my head is going to be in the upward direction, maybe here in that direction, but still, if I want my left hand to point to the surface, I'm going to walk like this. Do you see that? Everybody? Okay. So that's this. You'd sometimes even see, in fact, people adding on, it's a closed curve, that's why we added the circle on the snake. You'd sometimes even see people adding this on the circle, but it may or may not be indicative of the direction. So I would add the words. I would say counterclockwise or something like that. Okay. Good. And what is this? This we calculated, right? This is the curve in the xy plane, and it's the field F. So let's go to that board. It's this. It's precisely this. Only here we had it oriented the other way. Remember? It's precisely this calculation. So this calculation gave us minus 30 pi, but it was oriented the other way. So it has to be 30 pi if we want it oriented like in that solution. Okay? So this thing equals 30 pi because we just calculated it. Minus 30. Wait, whoa. I'm confusing myself. Let's verify this. So, right, you're right, because we had it minus 30 pi because of this minus here, right? So it's, the integral itself was 30 pi. It became minus 30 pi because of this minus, so itself it was 30 pi, but now we're going the other way, so it's minus 30 pi. You're right. Everybody got that? Confusing. Good? Okay, so it's minus 30 pi. Okay, and that is the integral over SA and SB, over what we're interested in, plus the lid. Okay, so the integral over SA, which is the question in the problem, of G dot ds, is, or plus this equals that, so equals minus this, the integral over SB, right? Minus 30 pi. Do you agree? And this we still calculated in part G. This is the integral of the purple, of the diagonal lid. And this was what? Minus 30 pi. So it's minus 30 pi. Minus 30 pi. And it's again 0. So there's a minus here, and this is by part G. And we get the same solution. And still there's work involved. Okay, it's all hidden, but good? Everybody good? Okay. So this wraps up this this review problem, which was, I think it really kind of touched a lot of things that we did in this course. We didn't, not everything, right? We didn't do any minima maxima considerations here, and we didn't do implicit function theorem, but most of the rest we actually did cover here. I think if you feel that you understood what's going on, and if you felt, better yet, if you felt that you would have, you would know what to do even before I wrote it, even if you realize that it's going to take some calculation, but you felt that you're thinking with me, then you're in pretty good shape. Okay, this is, it's not a hard problem. Okay, it's not, there was nothing tricky here. The numbers were really neat, and, but I think it's a good review. Any questions on this? Yes?
Shouldn't this one be smooth? Like,
no, for all the theorems that we had, Gauss, Stokes, Green, everything only required what we called piecewise smooth, which means it allows it to be comprised of a finite number of smooth whatevers. If it's surfaces, then smooth surfaces. If it's a curve, then a finite number of smooth curves that may be connected at points where, at those specific points, it's not smooth. Okay, so piecewise is in there in all these theorems. And that's important. This is not a smooth surface, evidently, because along the connecting line of SA and SB, it's not smooth. Okay? More questions? Everybody good? Okay, so I want to wish you a lot of success on your exam, and a lot of success on your other exams, and a lot of success in life. Okay, so that wraps up this class.